Hey guys, here's our model, Team 13's model for the scissor jack that we designed. We've organized our spreadsheet by kind of what certain pertains to. So over here on the left, these are parameters that we enter in. So you can see these are all just hard coded in. Over here, these are up the top. These are formulas for things that depend on what we hard coded in. Then we have our material properties. Notably, we have two different material properties. So that if we wanted to, we could have the diagonal number be one thing and have the crossbar be another thing. Right now, it's set up to just be all the same thing um, because that was similar as what we did for most of the time that we were exploring. And in this column, we have our targeted outputs. These are the things that we decided we wanted to, that we cared about. Obviously, you need to move 6 inches under 2,000 pounds, so displacement is a targeted output. We decided we wanted to optimize for weight for the lightest scissor jack possible. And we do care about the safety factor because this is going to be load bearing, potentially hazardous if it fails. So safety factor of 2 is what we're searching for. And we have color coded these things. I'll show you in a little bit here. I'll show you right now, actually. So if I want to change like my length of my diagonal number down to 13, then the safety factor is now dropped underneath 2, so it's turned red. It's not satisfying the criteria that we've set. If I set this to be 1 inch, then the displacement goes red. The weight goes negative because our member is 1 inch long and we have two half-inch diameter holes, so there's being more area subtracted away from the member by the hole than material that exists. So the total weight, since weight is just density times volume, and we've told Excel for our volume that it needs to subtract away according to the diameter of the hole, that we've got negative weight, which Excel recognizes as good because it's less than our target of 10 pounds, but in reality is not good. So there is a little bit of checking that has to go in there. But for the most part, color coding it makes this model really easy to follow, and you can see if a set of parameters allows you to succeed or not. And then over here, we have these are the forces that the member is experiencing that cause it to fail, and this is the force that you would need to apply to the top potential tensile force, 2,000 pounds modeled over here in order to cause a failure. And this is what the safety factor is looking at, saying, okay, how much bigger is that than the applied force? So the minimum angle here cares about, obviously, because the worst case scenario is what we care about. So the steeper this gets, if I have an angle of 0, then all of my forces go to infinity, pretty much. So probably about 20 or 25 degrees, maybe even 30. So the bigger that angle gets, the easier it becomes to not fail. But you do lose a little bit of displacement, like if we go back down to 0, maximum displacement went up 6 inches. That's great, but not physically possible. So the exploring that we did was just playing around with these different things. One thing that we kept track of was that we wanted to work with some sheet metal. So the thickness is set, and we just use gauge thickness charts to look at that. We validated this by having a version of this set up. Like normally the length of the crossbar is a function of the length of the diagonal number. Here we just hard coded it in so that it matched the homework, and our values came out to be what they were when we solved the homework. So that's pretty good. Going back to the material properties, we have a tab here with some different material properties of different metals, some steels, some aluminum, some titanium. Plug those numbers into here and watch the model update, see how that affects your failure points.